Anything between 1.2 and 6 months, up to 6 months, you can use zeta equals 1.2. And for 1 year, use 1.4. If the time is greater than 5 years or equal to 5 years, equal or greater than 5 years, zeta equals 2. That means your sustained load effect is twice as much as the instantaneous load effect. Okay? So that's very simplified. Actually, I don't know. I don't think IS 456 uses this equation. Does it? Do you know? Different manner. Exactly. But this is very simplified equation. Yes. Mm-hmm. Mm-hmm. Right.
But these coefficients are at lower side ACI. IS code higher side.
Okay. Okay.
In actual practices also, these coefficients are coming on higher side.
Okay. Mm-hmm. Okay. But this is what ACI tells us. And if you are designing FRP beams to satisfy requirements of ACI, this is what we will use. Okay. Now, because there is some difference between FRP reinforced beams and steel reinforced beams, there is some adjustments made, and that adjustment is given by a factor 0.6. Okay, so some adjustment is required because of the difference. So we have a factor of 0.6. So long-term effects, deflection due to long-term sustained load effect is 0.6 times zeta times delta I sustained load. So you first find out the deflection corresponding to just sustained load, not any other load, just sustained load. Plug it in here, and that will be your long-term deflection due to sustained load. Now we have two other items for today. So we have 10 minutes and two other items. So it should be okay. So in this, the two items are creep rupture and fatigue. So remember, I mentioned this previously. Creep rupture is due to sustained load effect. So if I have, if I apply a load on FRP bar and maintain that load for a very, very long time, okay, the failure will happen all of a sudden. Suddenly it will fail because of the sustained load. That failure load will be much smaller than the load at which we fail by static loading. Does that make sense? So if you apply static load, let's say you get 100 KSI or whatever that number is, 100 units, let's say 100 units. And under sustained loads, it may fail at 25% of that, which is 25 units. That's a big problem. So in your design, you must consider that creep rupture failure mode of FRP. Even in fatigue loading, similar effects can be found, or similar effects are normally seen. So we need to calculate the service load stresses and use those service load stresses to compare the stresses permitted under creep and fatigue loads for FRP. So for a given sustained load or fatigue load, we'll find out the stresses based on elastic analysis. Those are the stresses. And we have maximum limits. So you compare the two. So if the service load stresses due to sustained load or fatigue is less than, the stresses are less than the maximum allowed, then we are safe. If not, we have to change the design. That's the basis actually. So many times it's confusing to some people, of course. ACI 440.1 classifies creep rupture as a service load condition. Very important to remember this, or make a note of that. So ACI classifies creep rupture limit state to be a service load limit state. European standards, they consider the creep rupture as factor load effect. So If you are talking with somebody from Europe, they will just argue with you and say, no, but ACI is, we are using ACI, so ACI classifies creep rupture as service load effect, because that will make a big difference. It will make a difference of at least 1.5 factor, or it will be 50% off. So, and also in the creep rupture limits, we also have a factor of safety of 1.667. That's already inbuilt into the stress limit. So what we have to do first is to find out the stresses under sustained load, and that's based on elastic stress equation, which is moment under service load, S for service load, very important, remember that, S for service load, sustained load, service load which is sustained. So you have to calculate the amount of sustained service load moment, times NF is the modular ratio, we have that defined there, times D times 1 minus K. K we already calculated from our previous slides, and then I sub CR, we already calculated I sub CR from our previous slides. So this is what will give you FFS sustained load. Okay. So just to remind ourselves, those two equations for I sub CR and K, they look like this. I sub CR is based on K, K is based on this simple expression which has modular ratio, it has FRP reinforcement ratio. Based on these two equations, we can find out our actual stress under elastic condition. Okay, and it needs to be only for service load, and it needs to be sustained load. Creep rupture is for sustained load. Fatigue, maximum stress under fatigue loads is stress for fatigue loads. Two different things. So what are the limits? The limits are this: GFRP 0.2 FFU. AFRP, of course we don't use AFRP bars much, but CFRP is 0.55. This is where your design will be, don't mind my using the word, killed. That's it. So if I am to design something, I will start with creep rupture. Nothing else matters. Creep rupture will govern your design in most cases. So you will do all your calculations, you are ready to do your drawing for construction, everything. And if you check your creep rupture at that time, you will be in trouble because it's likely to govern your design. Okay? And then if you have fatigue in your fatigue load, that is cyclic loads, then they have oversimplified the design. What have they done? They said under fatigue loads, I may have a maximum stress of some amount, which is to be calculated based on elastic stress equation that we already looked at. And that maximum stress plus sustained load effect stress due to sustained load. So these two need to be combined. So this plus this will be compared with the 0.2 limit or 0.55 FFU limit for carbon or 0.2 for glass FRP. So that's what you will be doing if you have both sustained load effects and fatigue. Fatigue is a killer. It's really a bad, it's very difficult to manage fatigue and creep rupture in FRP reinforced beams. Something to remember. Once again, we will calculate our stresses by replacing MS sustained with movement due to all the sustained loads plus the maximum movement due to fatigue loading cycle. Okay, that's what we will need to use. So the good news is that's the last slide for today. But the bad news is you get a quiz. And of course, we also have an example. I initially thought I will go over that, but it's already 1:30, so we will end the session for now. But Dr. Das was very kind to print it for you, the example. Please review that example. If there are any mistakes, please let me know, because I finished that at 8:15 this morning. So there may be some mistakes. My main problem is I'm trying to convert PSI units to SI units. That's where I have to spend some time in fixing the example. Thank you very much. Do you have any comments or questions before I end? Yes.
Talked about bond-dependent factor
KB, yeah.
The recent version of a FIB model code, sir, no?
Yes.
From structural concrete,
Yes.
it says that whenever you want to achieve a crack control, you have to take into account the bond stress variation in steel, whether it is a linear variation or parabolic variation. But you suggested that bond dependent factor as 1.4. I want to know whether it is a linear variation of bond stress or parabolic variation.
It's based on test results and based on statistical analysis of test results. And for now, it is very conservative. 1.4 is conservative.
Why? Because FIB model code suggests two equations for linear variation as well as parabolic variation.
But ACI keeps it very simple.
It is suggesting only factor. So I want to include the bond stress variation is parabolic.
You can, but then you are dealing with ACI. Right? So, it's conservative, but at the same time, you don't know many things. So, what you don't know, you are always afraid to use. And if something happens to the structure, once you design it and build it,